In short, um, to kind of summarize, we talked about the fact that in general, most of the machinery that we have in machine learning that sort of like actually works, so to speak, or works in the sense of like is deployed in systems, or we uh, have sort of uh, you know yeah, almost any real world system actually driving machine learning or sort of slated to drive some kind of critical machine learning system in the real world depends either on supervised learning or sometimes very very rarely reinforcement learning. um, in either case we make certain kind of assumptions about stability over time. The reinforcement learning case is a little bit richer, but we usually assume that the reward dynamics and that the transition dynamics are static over time. um, in a supervised learning case, we really truly assume that the entire distribution of observations is static over time. And we started off with a lot of the motivation for why this is problematic. The fact that this sort of leaves you in the wind when there's anyone with sort of any conflicting motive that doesn't necessarily align with those of the system you're building, that has some ability to intervene in the data. So one example of this is the kind of threat models modeled by adversarial examples. We talked about the fact that just even in the absence of concerted effort to thwart your model, that there's just in general the normal state of affairs is that the world changes. So if you're trying to recognize things in radiology, equipment is going to continue to change and evolve over time, usually in a way that's from the standpoint of humans, usually equipment is evolving in a way that is beneficial, that is making the task easier. But from machine learning perspective, sort of any kind of change to the distribution is potentially sort of perilous. And models that seem to perform well at a task may fail at even what sort of semantically appears to be the very same task, just in a world where data looks slightly different. So images are slightly changed, style of writing is slightly different. And then we talked about how not only is this a really fundamental problem that needs to be addressed, but it's not actually a problem. It is many different problems, and that in general they are underspecified. So if I only give you data from the source distribution, and I give you data from the target distribution, and I just say it's labeled data from the source distribution, unlabeled data from the target, and I say do domain adaptation, that this sort of makes no sense by itself. Um, because there's multiple reasonable assumptions I could make that would sort of make this problem coherent, but each one is going to tell me something different about what the right thing to do is for how to make predictions in the test set. And not only is each one going to tell me something different, but each of these assumptions actually is like could in some a large subset of real world examples be reasonable. And so we took one simple assumption, which was, we looked at the label shift assumption, where we assumed that the distribution of labels is changing, but that's all that's changing. So the P of X given Y does not change, and showed how if you make that assumption, you're able to derive the machinery to detect shift, to estimate it, to correct your classifier on the fly. And you're able to do this quite effectively. And the challenge then is to say, well, uh, you know, that's great, but also what can we do for in general in the real world where these assumptions, or so facile assumption might not hold. And so there's been a lot of work. For example, one thing that we assume in the distribution shift work that we talked about in the label shift work, and that's also a standard assumption in classical works on covariate shift, is that basically the supports are the same, right? So any label, basically any example that has non-zero probability in the source distribution or in the target distribution also has it in the source distribution. And you see people, looking at data sets wanting to do domain adaptation in deep learning, and they have a data set and something like the source data set is photographs of products on white backgrounds from Amazon. And then the target distribution is something like photographs of those same products in the wild on arbitrary backgrounds and arbitrary lighting conditions. And these images have zero probability of showing up in source data. Source data is like a distribution that by definition consists only of images on white backgrounds. And so what, if anything, could be done there? I'll give an example of approach, a family of approaches that's kind of interesting, but also problematic, and where maybe the current like climate and ML community resulted in like thousands of papers adopting this kind of approach uncritically without thinking through the assumptions. Where I think a lot of these things could have been really obvious, and we could have saved a lot of time if we situated this in sort of things that we already know. So one kind of interesting intuition that came up in a paper in around 2015 or 2016 was this idea that we could sort of, this is, well, hey, let's say I have a big data set of images from one distribution. And so in this case, the paper doesn't make it explicit, I don't believe, but they're working under the covariate shift assumption, right? That we're basically assuming that if you fix an image, its label is the same. So you're working in a case where you're thinking of like object recognition, something like that. And the idea is, hey, I have a pile of images from source. I have some images from target. They look different, but I think they depict images from the same set of classes. How can I make a classifier that's going to leverage the unlabeled target data to predict well? To sort of develop a class, predict better than if I just threw the vanilla source train classifier at that data. And the idea they came up with is to say, hey, and there's a bunch of different variants of this. So there's Dan, there's ADA, there's a bunch of others. That basically says, let's learn a representation. Let's learn a mapping such that I can encode my data from the source distribution, and I can encode my data from the target distribution. And the hope is, let's encode them into a common latent space such that we can apply a classifier on top, like an adversarial, not really, okay, what makes it, the classifier from its perspective is just a classifier. It takes that representation as an input, and it just tries to predict which domain did this data point come from. So this classifier is trained both on the data from the source distribution and from the target distribution. During training, you grab batches of each, you feed them through, and this guy tries to distinguish, is it from source or target? Now you also train a model only on the source data, because you only have labels in the source data, where given that representation of the source data point, you try to predict what is the corresponding class label. And the idea is that you update the encoder so that the classification gets more accurate, but so that the domain classification gets less accurate. The idea is to domain confusion. You want to learn a representation such that the source data is classified accurately, but that the domain classifier gets confused. And the thought is that if the model was fooled so it couldn't tell the source versus target data, then you have somehow aligned the source versus target distributions. So I think at an level of intuition, this sort of sounds reasonable and it sounds kind of cute. And indeed, some of the experiments are kind of suggestive. That again, with domain adaptation, there's your data set becomes your data set size becomes, the effective data set size is not really the number of examples anymore, but the number of domains, and you're only looking at one or two domains. So it's a little bit of a funny kind of eval when you see a sort of out of domain evaluation. But the fact that you do so much better on some of these tasks seems a little bit intriguing. However, the authors also, they sort of invoke a lot of this work, a known result from learning theory from Scheib and David, which says that hey, when you're doing domain adaptation, there's a way to decompose, or not just to decompose actually, but to upper bound the target error as a sum of three terms. You're able to bound the target error by a sum of the source error, a divergence between the representations of the data points, and some more complicated third term. And what this work is doing is essentially minimizing the first two terms. This is, I want to lower my target error towards zero, my source error towards zero, and I want to shrink the divergence between the representations of the source points and the target points. So if you just look at it on its surface, it sort of seems like the idea sounds intuitive. However, the problem here is the theoretical justification that's given doesn't actually quite add up. And the reason why it doesn't add up is that minimizing the sum of these three terms is sufficient, but not necessary. So for example, it's sufficient but not necessary in the sense that it's possible that the optimal classifier actually has a representation such that divergence is actually large. It's just saying that if you were able to simultaneously set all these three things to 0, then the target error would be low. So this approach, it turns out when you minimize these first two terms, there exists a lot of problems where by minimizing the first two terms, you actually force the third term to grow really large. And the problem is that when the first term is 0, if the third term is large, that third term actually is an irreducible lower bound on the target error. So it's like by driving up that third term, you really truly are driving up the target error. And so you sort of adopt an approach. And the question is, you can step back and say, well, what assumption are they making? What actually makes it possible to do domain adaptation at all? And the answer is, well, the problem is actually underspecified because the supports are mismatched and it's not clear why we should expect the right alignment to occur. So this problem is actually more extensive than I'll demonstrate, but I'll just give one example of a clear counterexample that'll tie into the work we did yesterday. In work with my student Yifan Wu, and a similar result was seen in contemporary work by Fredrik Johansson, we noticed that when does this break down? And one way that this breaks down is actually when there's label shift, right? So even if the classes are fully separated, such that the covariate shift and label shift assumptions can hold simultaneously, what happens is that in the case of label shift, if you align the distributions in, imagine that there's 50% cats, 50% dogs at training, 80% cats, 20% dogs at test. If you've aligned the distribution such that the source and target data are indistinguishable in the latent space, that means that if your classifier is super accurate in source data, it has to be inaccurate in target data because it has to be predicting, way too few cats and way too many dogs. Because if it's predicting 50-50 on source data, it has to predict 50-50 on target data. Otherwise, it's not aligned in the latent space. So to give an example here, you could imagine, look at this diagram and see on the right that the only way you could align the source and target data, where in source you have 50-50 negative and positive points, and a right, the positive class dominates. The only way you could align these in the latent space is to have a latent space such that some regions of input space that are really from the positive class in the target data get mapped alongside points in the source space in the source data in the latent space. So we actually coming up with a way that guarantees you to get the right alignment requires some strong extra assumptions that it's not quite clear what are reasonable ones to make. But at the very least, we're able to modify those domain insofar as you think that there is something that's interesting happening in the domain confusion kind of approach. We are able to modify those algorithms in a way where it's still unclear when we should expect them to get the right alignment, but we can at least ensure that they're not guaranteed to fail in the face of label shift, and in practice get them to work. So in short, the approach is a kind of relaxed matching that requires that the support in latent space kind of overlaps, but allows that not that we have the density ratio has to be exactly 1 everywhere in latent space. It's allowed to be sort of looser. And so when we sort of relax this domain alignment criteria, then we're actually able to get results. You could see what goes wrong is on the left, the source data points are the blue and the red. And you see it's balanced classes. And now imagine that your target data was slightly shifted, and it was represented by these purple and green points. So in some sense, because there's overlap between the source positive and the source negative, the source positive and the target positive, and there's overlap between the source negative and the target negative, you think that it should maybe be possible to do something here, and these models should be able to recover the right alignment. But there's this added problem, which is the label shift. Notice that the blue and the red are 50-50. The green and the purple are like, 80-20 or something like that. And so when you apply off-the-shelf domain confusion approaches, they need to have the same number of points roughly in positive and negative. And we actually apply the approach with a neural network. This is what the domain confusion approach comes up with here, is in the middle, where it basically takes those green points and splits them across the classes just so that you can kind of match them in latent space. And indeed, when we use the relaxed criteria, we get something much closer to what we really want to get, which is that the green points and the blue points appear to be sort of matched in latent space, and the purple and the red appear to be matched in latent space. So this doesn't fully unpack the mystery of why and when, and according to what principles, the desired alignment should occur from these sort of domain confusion approaches, but it does at least identify and sort of remove one sort of failure case, or at least, empirically seems to. So the final thing I'll point to is kind of like a future direction that I'm currently doing a lot of work in and super excited about. And as you can see, my student depicted here in the bottom right corner is also very excited about, is this approach called, we call learning with counterfactually augmented data. And so the premise is, sometimes these assumptions like Y causes X or X causes Y are things that we can look at our data and actually we have a few enough variables, we can make these kinds of more like facile statements about simple sort of causal relations that hold, or simple structure. But with a lot of the kinds of data sets, there's a little bit of a chasm between in the causal inference world, we're talking about small numbers of variables or small numbers of groups of variables where we could make kind of sweeping statements about what is the causal relationship among them. And then the real world, like what's cool about the sort of causal thinking is that it gives you sort of, you can actually develop sort of like philosophically coherent ways of describing this broader set of problems, and maybe like mathematically coherent machinery for addressing it. But the problem, on the other hand, is that world is often, at least at present, not addressing the kinds of huge, messy, complex, like real world, high dimensional data sets where deep learning is doing some of the most interesting things. So for example, like raw text data, or, images even. So one interesting idea that I think a number of people are working on that we kind of really dove into a lot about it, maybe starting a year and a half ago, is this idea of saying, can we incorporate humans in the loop? And some of the things that we have trouble just explicitly stating structural assumptions, can we come up with ways to get human feedback that help us, sort of identify what we need to do to make sort of more robust classifiers. So we're not just motivated here by the conventional framing of robustness problems, but we're also thinking about things like in natural language that there's a lot of concern. People train a model, it gets high accuracy, and then they look and they find, okay, it was doing something, it was classifying resumes, but the model learned that to prioritize women, or to prioritize men, and to downweight female applications or something. It was sensitive to the gender words, and people say, oh, there's bias in deep learning, we should be very concerned. And indeed, we should be concerned about applying kind of technology in some wacky, like unfounded, incoherent way for problems which really are semantically very different from what it was trained for. But the deeper question here now, it's sort of, if we've gotten past the like, obviously there's a problem here, the question is, what is the nature of the problem actually? And we're discussing the problem in a very sloppy way. We just say the data is biased, the model's biased, there's we say it's learning spurious correlations, it's learning superficial correlations, it's learning all these, we come up with all these kinds of ways. It's learning the distractors. But it's not quite clear, like, what precisely does that mean? What does it mean for the data set to be biased? What does it mean for a correlation to be spurious? And, in statistics, there's one definition of spurious, right, that makes sense, which is basically you think you see a pattern, but it's only an artifact of a small sample size, and it goes away with a larger sample size. But I'd argue the problems here have nothing to do with sample size, what we're talking about in this exact moment here. It's not really about sample size. It's a different kind of spuriousness, and it's one that's not defined well at all within statistics. It's something more like the causal notion. So in causality, spuriousness is when you learn a pattern that sort of arises due to common cause. So like x1 is caused by something and x2 is caused by something. So you learn that they're correlated, but it's not because one causes the other or vice versa, but rather because they have common cause. And I think a lot of these problems, that's what we're concerned with, is that, so I'll walk through an example now. But the premise here is basically here. So I'll start with an example of, if you train a classifier on movie reviews, as I'll show soon, if you train a classifier on movie reviews, and let's just say like, we wave our hands a little bit. We use like a traditional model, like a TF-IDF linear model. We train it on movie reviews. We try to predict sentiment, positive or negative. What you'll find is if you then do like the kind of normal, kind of hand wavy data scientist thing of just train the model and then go back and look at the coefficients, and you just did this on like bag of words representation, and you say, what are the positive words? What are the negative words? The positive words, and I'll skip ahead here, you see words like great, fun, excellent, wonderful, but you also see words like romantic and romance, which are not necessarily saying it's a good movie. Romance is a genre, not a quality of the film. And horror, which is a negative, becomes one of your most highly negative words, right there with bad, worse, boring, awful, terrible. Even though horror is actually not, saying the movie's bad, it's just a genre movie. There's plenty of amazing horror movies, especially right now. So you see that there's a problem here, which is that the classifier finds these words that are correlated with genre, correlated with sentiment, but they're not actually like semantically related to sentiment. And so having worked on these domain adaptation problems and thought about it from the angle of identifiability, the question is, before you rush out and say, let's create the debiasing algorithm, the question is, can you actually debias this at all? Is it even identifiable which is the distractor versus which is the real feature without actually having some additional information? Is this something that is obvious just from looking at reviews alone? And what we sort of argue is that it's not, and that this actually requires some kind of structural knowledge, just like any problems where we want to depend on the causal features. So we can think of what we want to depend upon in some sense is we want the model to be causal in the sense that we want it to depend upon the features that actually cause the label to be applicable. So what we did is we created an annotation platform, and this was a huge amount of work for which 100% of credit of building all this infrastructure should go to my student. Is we built an annotation platform and ran a massive experiment with Mechanical Turk, and the normal annotation pipeline goes something like this: you write a review. You give someone a review, you ask them for a label. You give someone the text, you ask them for a label. And what we did instead is we said, here's the original review, here's the original label, which we already know. And below that review, here is an editable text box where you can, basically intervene on the review, edit the review. And here's a counterfactual label. And we want you to revise the review so that it agrees with the counterfactual label. And so basically we give them a few directions. We basically say the document should remain coherent. It should accord with the counterfactual label. So basically, right, it should accord to the counterfactual label. It should remain coherent in that basically, like, you shouldn't just change one sentence but leave contradicting sentences. It should, be a natural review. However, you shouldn't make any changes that are sort of semantically unnecessary. Like you shouldn't change any facts that actually aren't required to be changed in order to flip the label. So we're saying basically you should just make only the necessary interventions to flip the label from one side to the other, to flip the applicable label. And people come up with all kinds of creative ways. You might think that they just would like insert negation in random places. That's always a concern. You know, they're just going to say this movie is not great. But actually, people come up with all kinds of clever ways. They revise the reviews. They change adjectives. They modify the grammar of a sentence to make it look sarcastic. They they replace some modifiers. They kind of come up with like little ways of tempering claims. So the movie goes from becoming more and more intriguing to only slightly more intriguing. And so there's a number, the humans are actually quite, creative here, which is interesting because I think there's been previous studies where people ask people to generate text on the spot and they lament that people are rather uncreative and homogenous. And I think part of that is maybe just that it's a lot of pressure and maybe too out of the blue to just ask someone to generate text randomly. But when you give them this prompt and you give them this task, people are actually quite creative. And I showed you before what it looks like if you train a model on the original data. If you train the model on remember, so we had the original data, then we created a data set where we have basically what we call the counterfactually revised data. For every original data point, you have a corresponding data point with the opposite label, where only the things necessary to be changed have changed. So for every positive review, you have a new negative review. So interestingly, if you look at this plot, if you train on the revised data only, but not the original data, bad, worst, boring, awful remain negative words, and great, fun, excellent, wonderful remain among the top positive words, but horror and romance actually flip. Romance becomes one of the most negative words, and horror becomes one of the most positive words. And the reason why is because horror was, basically present in almost only negative reviews or majority negative reviews before. But in the revised data, all those reviews are now positive reviews, but they still contain the word horror. And so basically what's happened is the human has given us information by virtue of which things they did or didn't edit. So by the fact that they didn't edit certain words, they've revealed to us that these aren't the causal features. So when you take the original data, you get this, those features all sort of matter. When you take the counterfactually revised data, those features all matter but have the opposite effect. But when you combine those two data sets together, which is the old plus the new, what we call the counterfactually augmented data, you suddenly find that those words fall out. And not just those words, but you'll notice back here, there were these other words like seems, both, life, has, my. So there were a few other words, will, that weren't actually sort of relevant, obviously, to sentiment. And it's interesting to see every single one of them disappears from the data set, or disappears from the set of so-called important features. So I think it's here where I guess the main thing that I want to communicate here is that we're not even able to formally express the assumption, but the fact that we maybe have the experience working with structural assumptions and thinking about questions of identifiability, I think there's a lot of opportunity, even in places where you can't necessarily apply, the fully coherent mathematics of causal identification. I think there are still cases where you can apply causal thinking to do something that design procedures to inspire research that at least borrows the qualitative ideas, if not all the mechanics. So an interesting thing happens quantitatively if you train on the original data and evaluate on the revised data. Then your model goes from really good to really bad. If you train on the revised data and evaluate on the original data, your model goes from really good on the revised data to really bad on the original data. If you train on both of them together, the model actually does really good on both of them. So at least in this case, what it's saying is you can get it does slightly worse than the model that's specialized to either, and that makes sense because it's not you're not relying on you don't have how should I put it? There is predictive value there actually is predictive value in these sort of spuriously associated features, right? They are predictive. They are associated. And so any sort of, optimal estimation procedure is going to use them. However, the point is that while you pay a tiny cost for making a model that's sort of insensitive to those, it's actually, that cost is tiny, like it is small. Your model, in this case, rather than getting 87%, and 88%, we get 84, and or in this case, we do better on one of those data sets. It goes back and forth depending on but the point is like maybe pay a couple points accuracy on one of the data sets, but you get a model from the combined classifier. Well, I know it's okay. It's the same pattern, just the lines are slightly flipped. But anyway, so that's the key thing, is that you were able to get a model that performs surprisingly well on both, with almost only a tiny cost, maybe 1 to 3 points in accuracy. So at a high level, that the main thing to communicate that right is we are always faced with distribution shifts, that where there's a tendency of us now to sort of that I think it comes from a pattern of research that works in supervised learning but doesn't really work in general for all classes of problems, which is just try stuff and see what happens on the benchmark. This doesn't work on a task that fundamentally is without a benchmark. And that the only way we can sort of do things that make sense is by incorporating some kind of structural knowledge. It's the only way we can deal with game theoretic type situations, with causal inference type settings, with domain adaptation type settings. And one frontier, I guess, that I would kind of end here that I'm excited about is both how do we develop that sort of fundamental theory of leveraging formal structural assumptions, but also how do we maybe use that work to inspire sort of maybe a more creative line of research that at least incorporates the thinking into all kinds of other areas, including human in the loop learning. So I'll end there. And
perfect. Thank you,
this
Simon.
could, I guess, be we still have some time for discussion.
Yes, exactly. And actually, there are quite some questions that have been collected throughout the days. So we'll start with the more popular one. The most popular one says, which techniques allow to incorporate the feedback loop concept to machine learning architectures or pipelines?
So there's a lot of the challenge is feedback loops can arise in very complex ways, and many of them so super complicated social settings are extremely hard to model. There's not just like a sort of facile thing to point to, but there certainly are lots of approaches where, for example, that have begun to like formalize these problems and look at these feedback loop problems, and try to develop sort of modifications to the standard algorithm. So one good example is work in recommender systems. So in recommender systems, there's a problem, which is that you look at a set of tuples of like user item rating, right? And more often, even people look at what tends to be more useful even is looking at passive feedback, things like user item and some measure of like purchase, no purchase, or and the problem is the feedback loop there is you use the data on who purchased what to modify the recommender system, but the recommender system influences who purchases what. So you change the recommender system, people purchase something different, then you fit a different model, then you run it in the wild, people, you influence their behavior again, you get a different set of traces, not just different examples, but actually like distributionally different. You keep training your model, and right, it's not just that things are changing like in a way that's like exogenous, it's changing like the world might change exogenously, and we're sort of okay with that. We have to anticipate that, but we don't want to be the cause of the change. Like we don't have like these self-confirming models. Like you recommend people, everybody should look at this, one Twitter account, and then a lot of people click on it because you recommended it, and then you say, oh, people seem to be liking this Twitter account. Let's recommend it more, and then people like it. So one thing that people do is they try to modify this systems for learning from these kinds of feedback with things like borrowing ideas from sort of like causal inference and domain adaptation, and using things like inverse probability weighting on observations to account for the exposure bias from the previous set of recommendations. So there's a line of work that I think could give you a lot of inspiration. Is there's a great researcher who's also a great human, and I recommend if you have an opportunity to work at Microsoft Research in Seattle that you take it and try to work with him, is Adith Swaminathan, and his doctoral work with Thorsten at Cornell. They did a lot of this work where they sort of developed kind of coherent ways of sort of accounting for these kinds of exposure biases to modify sort of like standard matrix factorization type recommender system algorithms. And in general, I think Adith has been thinking really deeply about these kinds of problems in the context of recommendation, in the context of search in general, in these kinds of like customer interacting type settings. Another place where I look where it's maybe not as much at the point of like, here's a machinery that I would take and just apply off the shelf, but more like, let's characterize the situation, is a lot of people have started to look at economic models. So these are kinds of problems that, economists are maybe tend to be better at talking about and thinking about and casting formally, where I think like the ML and econ communities are maybe sometimes talking past each other. Like ML, we only think about prediction, but we're really good at actually building products and actually thinking about fitting our models on real data. The economists want to actually understand the mechanism, but maybe are usually, not as good at touching the real data and building systems. And so we just sort of saying like, oh, their field is, old and crusty and isn't doing whatever. And they look at us and they're like, these idiots don't, they don't even know what the problem is they're addressing. So in econ, in general, they think about things like dynamic games, right? So once you actually model the other agents as being independent agents who are responding strategically to what you're doing, this suddenly has a flavor of like a game theoretic type problem, right? And when you have repeated games in time, this is like a whole kind of advanced field. It has a little bit of a flavor of multi-agent. It's a lot of ideas, in general, like between like machine learning operations, research, economics, whatever. There's a whole bunch of topics that are highly overlapping, where maybe we're not even always so aware of just how deep the overlap is, both in like Markov decision processes and bandit type algorithms, and here in the like multi-agent type learning. One area that I'm kind of excited about these things starting to show up is a lot of the literature on like fair machine learning. I think, for the first few years, suddenly the ML community started to become taken with these ideas of questions of, as people got concerned specifically about like the misapplication of machine learning in contexts like criminal justice and lending and hiring. People started to think about these questions of, what if we really want to understand the impact of a machine learning on social system. We don't just want to know like, did the classifier classify people more one way or the other? What we want to know is what actually is the long-term effect of making predictions the current way versus if we do something different. Like imagine, you're talking about anything, whether it's school admissions or hiring processes or whatever. What you want to know is if I intervene in a system, am I actually in the long run making people better off, or am I making people worse off? Like making things fair in a way that you call fair that actually harms the people you're trying to protect isn't actually all that, beneficial to anyone. So there's been a lot of work, some interesting work from, I think Lily Hu was one of the first people talking about this. Moritz Hart in his lab at UC Berkeley does a lot of work that I think is really interesting and addressing stuff. I've tried to work on some of this in my own work, especially in collaborations with Alex Choltachova at Carnegie Mellon. And who else is working in this space? I think Aaron Roth and Michael Kearns and have been doing some interesting papers in this space, where the the thrust of a lot of the work is trying to model. You make a set of different predictions, but so here's an example. Would be um, uh, uh, so Moritz Hart, I think, especially with his students, Smith and Milley, has some of these papers where they look and they say, like, okay, you make a different decision in terms of who you grant loans to, but then just to like model the next step of the process of given somebody's certain characteristics of somebody, and given the kinds of loans they get or whatever, and their actual likelihood of repayment, what happens to, say, their credit rating and all these things that like affect them, in the next round, and then they might need to apply for a loan subsequently. Are they better off or worse off? So like modeling that fact that like you don't solve like if you look at a broken economic system where there's massive inequality, and then you say, what is the how do you solve it? And it's like, naively you might just say, okay, let's just take one group of people that's sort of economically poor, very well off, another group that's not, and let's just grant large loans to them, but at equal rates. The danger of doing that is that can also sort of look like predatory lending or something. Like making huge loans to people that can't repay them back isn't necessarily making them better off. And so, there's a lot of work just trying to cast simple kind of economic models that, allows to at least qualitatively begin to interrogate those things. Now, the problem there, of course, is that real world dynamics are really complicated and rich. And it's ultimately, in order to interrogate these questions, we can't just do it in a wet lab. We can't just actually go in the real world and just start, denying people loans and giving people huge loans and seeing like what happens to them after they go bankrupt, and trace and do an experiment to analyze it. So we start studying these things through oversimplified models. But the danger of modeling, like the good thing about modeling is it allows us to say, how do assumptions map onto implications? The bad side is that we, when you have a very like epistemically uncertain field, how can you be sure that you actually captured all the important facts to do the modeling? So I'm going to leave it there because I think we don't have that much more time. I think there's other questions, but hope that gives you some pointers.
Well, it's a bit connected, the next one, and it has to do with your publication that you had on bad practices in machine learning research. It was quite influential, but then it has been already some time since this was published. So what do you think has improved? What remains to be improved?
I mean, I think there's an interesting thing happening, which is like, I think net, I think net, there's some sense in which things have just gotten worse, because it's like, I think the driving forces are like a set of incentives, which is like people, I think so I think a lot of like, there's a few things going on, right? One thing that's going on is that science is hard. So it's very easy to communicate how to use TensorFlow. And I think there's a whole generation of people that grew up. There was a moment in time where like training a neural network to do X, and then like just seeing that it could do it and reporting the number, or just like, making the neural network bigger and then saying, okay, the number went up. That really was interesting science. The reason why is because the results were unknown. Like it wasn't obvious that the stuff would work so well everywhere. But the problem is, it's like, for a group of people that has such a narrow like experience of science, that's the only science they ever knew, they think like that's this is what it means. Like this is what research is. It's just backprop, and that's like the only thing that needs to be communicated to disseminate research, democratize it, is disseminating the ability to do backprop. And so like libraries like PyTorch and TensorFlow, it's something have massively expanded the community. But the kind of like, I think, scientific mentorship, the like one-on-one communication of like intuitions and values and integrity, right? The bar that you hold yourself to, of basically like, when we submit a paper, we like to, and I can't say that every single time, in every single context, and obviously especially when you have there's countervailing considerations, like there's young people who are learning and you want to support and everything. But for the most part, what we at least strive to is to be in a situation where like no one should have been more critical about your work than you were. like when you get to the reviewers, they should actually seem kind of tame compared to what was happening when you were developing the idea. Um, and communicating those values, I think it just doesn't scale. It doesn't scale. Like, and a faculty can't, I think, grow a lab beyond 10, if you're superhuman, maybe 15 people, and continue to promote it. So in a sense, like, as just like the more and more research is being like kind of like so on one hand, it's great that the community is growing, but I think as like both the researchers and the reviewers are sort of like this sort of massively expanding base that's sort of like on the balance, less experience and like less exposure to that mentorship. I think that some of the kind of like just sloppy practice has expanded. The other thing is that I think the other driving factor is like the economic environment, that papers, one, are largely anonymous. There's how many hundreds of thousands of papers submitted in deep learning every year, across not just the core conferences, but across the universe of research. Probably like hundreds of thousands, given like the sort of like bibliometrics, around it. And when so there's maybe two things. One is that when you have that kind of environment, for most people, you have so many people in positions where a very cynical thing could happen. Like, it's not like you're in like 1900 and there's like 500 physicists in the world and almost everyone is going to read everyone's work, and you'd be very embarrassed for somebody to have a paper accepted and it turned out that you were wrong, or that you were and maybe that's even too conservative, but you get the idea. It turns out that you were not just wrong, but like you were you know basically like you just didn't even have a result. Like, you were just like, ship it to the conference. Let's just see what happens. Ship it to the, like I think the depersonalization of the experience of interacting with a paper, and then this combined with one additional factor, which is the economic environment, that machine learning has become so lucrative. It used to be like the reason to get these publications is so you could be an underpaid member of this like small academic club. And now the reason to get this paper is often a commodity. So you see this happening all the time, where people like, I've had these conversations. I've seen these conversations with young students. It's like, this paper is not ready, and they're like, but I need this in order to get the job that I want, or I need to have, that's like the timing. I need that, and it's I think that like overall the because like the standards, I think, gone sort of adapt, but yeah, I think in a way things have like gotten so loose. um it's sort of created a kind of like credential inflation, that everybody has these papers. Now everybody has these papers, and you need to have even more of them. And the combination of that with the fact that nobody's actually reading the papers, when they're certainly like, it would be, it's bad enough, I think, in things like, say, admissions processes and stuff, where people are reading through tons of applications, and a lot of people have published, and with the credential ends up being more that they have published these papers at that venue than like I think at least too often ends up being. I think there's plenty of people who do a good job and read them, but I think it's only worse in like maybe industry jobs, where people are seeing it as this commodity. um so that's like the bad side of the picture, which is, I think that the community has still kind of continued to sort of like have these sort of economic conflict of interest, the anonymity of the papers, that like I think leads people not taking the appropriate pride in work, and the kind of overall like um, failure of the mentorship to keep pace. On the other hand, just speaking from like within the university, I do see a lot of positive signs. And I think one of them is like a growing awareness of what's happening, and a recalibration of values, and of sort of like goalposts, to like not like we I think have been in the last, I'd say if you were to compare right now to like 2018 or 2017, I think there's been a bit of a pullback in a lot of, at least the labs that I really respect, of like you like really like against thinking of like against kind of the way of talking and thinking of like the value system of like number of papers. um And trying to push back, I think, on the overall kind of tendency to, you know, whatever this is, this kind of like gold rush mentality, and to sort of, one thing about the, um, if you look back, okay, on one hand, the papers become anonymous, and when they become anonymous, and people start thinking with that mindset that no one's going to read it anyway, then they start spamming things. But on the other hand, it makes it suddenly, when there's so many papers that nobody's reading, it almost makes it's way more prestigious in a way. In a world where there's like 10,000 or 100,000 people who have like NeurIPS paper and ICML paper or whatever, a CVPR paper, it, I think, suddenly becomes much rarer to have a paper that people have like read and respected. And I think like I do see movements, at least within certain labs or within a subculture with machine learning, of pushing back and trying to correct this. But it's it's a huge challenge. It doesn't happen overnight. I'd say, like, I think I give more credit to the community. I think, okay, I think there's a subculture that's pushing back. I think the leadership of the community is pushing back. And I think there are a lot of great people in the leadership of the community. You know, so I see this, for example, in attempts by, like, I think ACL, I think NeurIPS this year. I think a lot of conferences are trying to um, be more thoughtful about how they give directions and communicate values to reviewers. I also think they're doing it both in the form of like official documents and training, but also in even like trying to make changes to the review process. Um, I also see people just experimenting a little bit more with the process and trying to come up with alternatives. I think there's been an interesting like breath of fresh air into the journal system. So I think, for example, the kinds of sloppiness in communication, and sloppiness, or outright negligence in review that you sometimes see at conferences. I've reviewed for JMLR for many years now, and I'd say that I've never seen the kinds of reviews that are like the really like pathological reviews. I've never seen them at JMLR. In general, I've always been very impressed by the overall quality of the process. Not to say that there's no noise or that nothing wrong gets through, but no process has that. But I think it is a push in the right direction. I think it's also, perhaps with the awareness of the noise of the system, the journals that like JMLR or tackle in the context of natural language that maybe have maybe a slightly like better reputation in these respects, I think have actually, like, their sort of value as like their currency in the community has gone up, and I think that maybe also maybe shifts the balance a little bit. So I think these are very gradual processes, but at the end of the day, I think this is research values are communicated through mentorship. Um, and I think the best way to do this is to hold yourself to a high standard, to work with people whose work you think meets that standard, and to pay it forward. Like to when you have interns, when you have students of your own, to set the right values, to say, like, to be able to say it's okay. Like, I don't care if we make this deadline. Like, use the deadline as a motivator, but like this is what it takes. Or no, we can't write that because it's wrong. Like, it doesn't matter if you like the way that sounds. It doesn't matter if you think it's a cool name for an algorithm. It doesn't make sense. We're not going to put it in the paper. um, or um, when someone says, I think okay, it's not right, but like, I think, if we put this result, I think the reviewers aren't going to like it, or if we compare to that thing, we're not going to look good. To be like, this is across the line. Like, this is not something that we're going to engage in. I think, um, you know, we can slowly move the needle.
Great. And last words for any young researcher: what can this person do to be better at her research, be more critical, and not run into these pitfalls?
Like, it's time to try to come up with like a specific, directive, like, just do this. But these problems are so diverse, right? I think the biggest thing is integrity. Like, and it's not to say, so I think, I think the biggest thing is to 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 actually aspire towards it in the first place, and to like really make an honest effort. Like the actual specifics of what to do, it's like, okay, you could read the things that I wrote, you could read the things that other people have wrote, you could disagree with some things, you could disagree with things, but you should have an honest conversation about research value, and you should think about it seriously. Like I would even encourage people to like think a little bit about the process of science and not just like what they're doing right now. Like read not just read like my commentary and some other people's commentary about the current state of ML, but have some maybe awareness of like scientific method, and like Popper and Kuhn, and like think about how does science perceive what are important questions, what is the right way, what are the methods of like by which like knowledge is actually created, what is are honest and dishonest ways of doing things, where should the bar be, and then to just like actually hold yourself to that. I think so much of it is just like uh has become a bit of a cliche, I think, for like everything from you know um yeah, but it's like I think the 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 cliche way to put it would be like you have to do the work. I think like here the work consists of, I mean, I see so many papers where it's like, like even before you get to all the things that are wrong from like a scientific standpoint, or experiments or comparisons that ought to be there that are avoided, or things like that, you get to like the manuscript doesn't even like a lot of papers, you read the manuscript and you realize that nobody has read that manuscript before. And think about how crazy that is. Like I want people to like appreciate, because I think this happens all the time. Like a paper gets submitted that was written in 3 days before the conference deadline, where literally no one has read the manuscript. And by read the manuscript, I don't mean that nobody like saw the word at the moment that they were writing it, but I mean no one actually sat down and read the paper from the beginning till the end. Is this something I try whenever possible, and certainly for any project that's like I have a deep involvement in, like with my PhD students, I almost whenever we make it work, we try to spend like an open-ended block of time,
Yes.
even after the draft is already in good shape, and go through it literally line for line. And I
Yes.
think when you start doing that, when you actually interrogate your own work, you read it critically, you you start thinking, okay, every single sentence has to make sense, has to be perfect, has to be spelled correctly, has to be grammatical, has to mean what I think it means, has to, the paper has to be organized, whatever. I think like a lot of other things just I think kind of flow naturally from a certain degree of like being thoughtful and being invested.
Well, we can summarize it as in a researcher should give her paper for others to read before submitting it. And now we have run out of time, so we have here already Maria. So,
They should read it themselves too.
yes, that's a good point as well. Um, so it has been a great session with you, Zach. We have covered a lot, not only of machine learning, but more of general best practices as a researcher. And I'm sure that the audience has learned a lot for these past couple of days. And well, I imagine that people can find you on Twitter, on your email, and then contact you with questions. There were many questions that we did not cover. So probably there will be quite some people who will be contacting you and inquiring more about your opinion on these matters.
Cool. Awesome. Looking forward to chatting some more.
Well, then, thank you very much, Zach.
All right. Take care.
Have a nice day.